Okay, so here comes the next couple of questions, starting with number 5. So if we want this thing to be differentiable, the first thing is for a function to be differentiable, it must be continuous and the slopes coming in from both sides have to match. So the first thing that I would say is that if I try to approach the function f from 1 from the left side, it has to be the same as if I try to approach -1 from the right side. That's the first little piece of the continuous thing, is that the limit from the left, the road in and the road out, have to be the same. So as I approach the number -1 from the left side, which would be this bottom piece, I would actually, as I get close to -1, I would get b. As I get close to -1, I'd have 3a plus 4. So I literally am just plugging in -1 into each of these values. -1 squared is 1 times b. -1 times -3 is 3a, 4. And that somehow has to be exactly the same as if I plug it into the top one, which is going to be -a plus b. Now, what that actually led me to very, very quickly is to see that I could cancel these two b's out, move the a across, and I'd have -4a. And I just found out that a somehow has to be precisely -1 for that to happen. So before I even really proceed very far into this problem, I already know the value of a. But in addition to that is that if I were to take a look at the derivative of the function, the derivative of ax plus b would just be a for values of x above -1. This one would be 2b minus 3 for x values below -1. So again, if I were going to take the limit as x approaches -1 on f prime, it should be the same as if I do -1 on f prime, whether it's from the left side or the right side. So again, as I approach the values from the lower side and I get really, really close to -1, I just have 2b minus 3a. Notice that in this case, it would be 2bx. So as I get close to -1 on the left side, I get a -1 times that is a -2b minus 3a. And somehow that is supposed to be the same as the derivative from the other side, which is just plain old a. So that means -2b has to be the same as -2a. But I already know, according to the information that I have right there, I feel like I have made some kind of a mistake here. I got a -2b and a -3a, and that's equal to a. If I added 3a to both sides, there's my mistake. Let's fix that before I keep going. If I added 3a to both sides, I got 4a. And so that means b would be -2a. So if a was -1, then b has to be +2. So I now know what a is and what b is. So my function f of x, let me pull this back up here to the top, is no longer ax plus b. It was ax plus b. And the second one is bx squared, 2x squared, minus 3ax, so that'd be plus 3x plus 4. And this is again for values of x greater than -1, and this is for values x less than or equal to -1. And that's what actually makes this function continuous and differentiable. Now, that was the hard problem. Number 6 is a much nicer one. The places where it's not going to be differentiable has to do with a. Now, the reason why it is not differentiable at a is because to be differentiable, it must be continuous, and it's clearly not continuous here. So a, discontinuous. And what you could say to demonstrate that is the limit as x goes to 0 from the left side is not the same as the limit as x goes to 0 from the right side of f. Hey, Victor, come on in. Now, what I can secondarily say is that b is not a good value because the limit as I approach the number, I guess this would be probably like, say, 2 from the left side of f prime, is not the same as the limit as I go to from f prime on the other side. Again, the derivatives have to match from both sides for it to be differentiable. C, we definitely have a similar problem as B. So same argument as B. Notice that there's a sharp spot. The derivative here is different from here. And our last problem is at D, right here. And the problem is at this place is the slope of the tangent is vertical. Is vertical. And that kind of finishes up that particular question, number 6, and I'll be back with the next video shortly. All right, have a good one. I'll be back.